When we count ordinary objects, we have certain words we use to make counting easier. For instance, when we talk about our shoes and socks, we always talk about them in terms of pairs. I have 4 pairs of shoes and 12 pairs of socks. A pair always means 2. We usually buy eggs by the dozen. A dozen means 12. I can buy a ream of paper, which is 500 sheets. We use these kinds of counting words, pair, dozen, ream, for specific situations. You wouldn't ask for a pair of eggs or a ream of eggs, and you wouldn't ever ask for a mole of eggs. That's way too many eggs. But a mole makes sense if you're talking about particles in chemistry. A mole is another counting word, like a pair or a dozen, but it's used to count a very large number of objects, 6.02 times 10 to the 23rd objects. Now when I say objects, I mean atoms, or ions, or formula units in the case of ionic compounds, or molecules in the case of molecular compounds. Those are all what we call representative particles, the smallest unit of that material. 1 mole of helium is 6.02 times 10 to the 23rd atoms, because helium is atomic. Hydrogen is molecular, and it exists in nature as a molecule of H2. So when we say 1 mole of hydrogen, we mean 6.02 times 10 to the 23rd molecules of H2. 1 mole of NaCl means 6.02 times 10 to the 23rd formula units, because NaCl is an ionic compound. 6.02 times 10 to the 23rd is known as Avogadro's number, named for the great Italian chemist Amedeo Avogadro. Although Avogadro did fundamental work on atoms and molecules, he didn't actually come up with this number. It's just named in his honor. They must have thought pretty highly of Avogadro, because Avogadro's number is huge. It's used in chemistry because the particles in chemistry, atoms, ions, molecules, are so tiny that there will be a massive number of particles in any appreciable amount of a substance. If we're going to talk about the number of atoms on the head of a pin, or the number of molecules of a liquid in a beaker, we need a really big number. But why 6.02 times 10 to the 23rd? Why this number, and not 20 billion or some other giant number? 6.0221421 times 10 to the 23rd is the number of atoms in 12 grams of carbon-12. Carbon-12 has historically been used as a standard in chemistry. For instance, we use carbon-12 as the standard for atomic mass. So, Avogadro's number is not completely arbitrary. For ease of use, we typically round Avogadro's number to 2 decimal places, 6.02 times 10 to the 23rd. Let's see an example of how to use the mole. We have a beaker full of water. If the beaker has volumetric markings on the side, it's easy to measure the volume. The beaker contains 400 milliliters of water. If we have a balance, we can measure the mass of the water. The beaker contains 400.0 grams of water. But what if someone asked you how many molecules of water are in the beaker? We'd have to do a little calculating, and that's when we'd use the term mole. If we want to convert from grams of water to number of moles of water, we'll use the molar mass. The molar mass of water tells you how many grams there are per mole of water. To find the molar mass of water, H2O, sum up the gram atomic masses of the individual atoms from the periodic table. There are 2 atoms of hydrogen and 1 atom of oxygen, so 2 times 1.008 grams per mole plus 1 times 15.999 grams per mole equals 18.015 grams per mole. Rounded to 1 decimal place, we get 18.0 grams per mole for the molar mass of water. Let's convert from grams of water to molecules of water, using the molar mass we just calculated as a conversion factor, and Avogadro's number as another conversion factor. 1 mole of water equals 6.02 times 10 to the 23rd representative particles, in this case, water molecules. Start with what we know, 400.0 grams of H2O. Leave a space for our conversion factors, and write the units we want to wind up with on the right, molecules of H2O. 400.0 grams of water times 1 mole of water per 18.0 grams of water times 6.02 times 10 to the 23rd molecules of water per 1 mole of water equals some number of molecules of water. Grams of water cancel, and moles of water cancel, leaving us with molecules of water. 400.0 times 6.02 times 10 to the 23rd divided by 18.0 equals 1.3 times 10 to the 25th molecules of water. For solids and liquids, this is the most common kind of conversion using the mole, between mass and number of particles. For gases, you can convert between volume and number of particles. This is because of a peculiar property that is true of gases at STP, standard temperature and pressure. STP is 0 degrees Celsius and 100 kilopascals. Under these conditions, 1 mole of gas equals 22.4 liters. It doesn't matter if it's a mole of hydrogen, or helium, or argon, any gas you want. A mole of gas measures 22.4 liters at STP. It's weird, but true. Let's see an example of a conversion that uses this fact. A neon sign holds 200 milliliters of neon gas. How many atoms of neon is that? And how many grams does the neon weigh? Assume STP. Start with what we know, 200 milliliters of neon. Leave a big gap for conversion factors, and end with what we want, atoms of neon. We'll need several conversion factors for this problem. First, we know we need to go from milliliters to liters, so we'll use the conversion factor 1000 milliliters per 1 liter. Make sure the orientation of your conversion factor is correct, so units cancel. Next, we'll use the strange but true fact that gases are 22.4 liters per mole of gas at STP. Then, we'll use Avogadro's number to get the number of representative particles. Neon is atomic, not molecular, so in this case, the representative particles are atoms. 200 milliliters of neon times 1 liter per 1000 milliliters times 1 mole of neon per 22.4 liters of neon times 6.02 times 10 to the 23rd atoms of neon per 1 mole of neon equals some number of atoms of neon. Check to make sure our units cancel. Milliliters cancel, liters cancel, and moles cancel, leaving atoms of neon. 200 times 6.02 times 10 to the 23rd divided by 1000 times 22.4 equals 5.4 times 10 to the 21 atoms of neon. Now what about the next part of the question? Given this number of atoms of neon, how many grams is that? We can use the molar mass of neon from the periodic table. and Avogadro's number as conversion factors. 5.4 times 10 to the 21 atoms of neon times 1 mole of neon per 6.02 times 10 to the 23rd atoms of neon times 20.18 grams of neon per 1 mole of neon equals some number of grams of neon. Check to see your units cancel. We get 0.18 grams of neon. Based on our experience with these examples, we can draw a map that relates all these kinds of conversions. To go from mass to moles, or moles to mass, use the molar mass, grams per mole. To go from the number of particles to moles, or moles to number of particles, use Avogadro's number, 6.02 times 10 to the 23rd particles per mole. To go from the volume of a gas to moles, or from moles to the volume of a gas, use 22.4 liters per mole. Remember, this one only works for a gas at STP. You can see that the mole is central to solving all these kinds of